Tonight, you and I will gaze into the deepest questions in physics, where reality might not be what we see. I spend my nights studying stars, but today we explore how quantum math points to a multiverse. Not as a sci-fi dream, but naturally from the exact equations I use to track celestial bodies. So take a slow breath, relax, and step with me into the quiet, unfolding mystery of the vast quantum multiverse. Chapter 1: What exactly is a multiverse, and why do stargazers like me care? The idea of a multiverse remains one of the most beautiful and fiercely debated concepts in astronomy today. To most folks, it sounds totally made up. The idea that countless other cosmos exist right beside our own, each holding its own distinct version of reality. You might picture shifting timelines. Others imagine totally weird laws governing their own distant stars. Yet this thought doesn't just sprout from late-night campfire tales. It flows naturally from our most rigorous space science. Here, I will walk you through what we researchers mean by the multiverse, and why so many of my colleagues see it as a true cosmic possibility. Though the idea bends the mind, its foundation sits deep in proven physics, especially quantum mechanics. Let us start with a simple definition. For generations, universe meant everything in the sky. All matter, energy, dark space, and time itself. So how can anything exist beyond everything? When my peers talk about a multiverse, they mean the night sky we observe might just be one tiny neighborhood, a single patch within an infinitely grander collection of swirling realities. These hidden domains could be completely cut off from our own, or they might be subtle variations born from the exact same primordial cosmic spark. There is not merely one single type of multiverse theory. Honestly, there are quite a few, each blooming from different branches of theoretical physics. A very early hint came from cosmic inflation. That is the theory suggesting space itself stretched out incredibly fast right after the Big Bang. In many reads of this model, that massive outward push did not stop everywhere simultaneously. Rather, it kept going in distant pockets, blowing up bubble universes. Each expanding globe could grow uniquely, forming weird new laws and particles. Through my telescope, everything we see is just one single bubble drifting through an endlessly expanding void. Another path to a multiverse opens through string theory. It is a beautiful math framework trying to bind all natural cosmic forces together. String theory refuses to map just one lonely cosmos. It points toward a staggering number of potential solutions. Each of these answers represents a totally unique way space and fundamental physics could be organized. Some numbers hint at 10 to the power of 500 ways the math could unfold. Every single one of those could birth an entirely separate universe, glowing with its own distinct reality. But stick with me here. You and I are going to focus on a different multiverse tonight, one born entirely from quantum mechanics, the strange study of the ultra-small. In quantum rules, particles don't just bounce around like tiny planets. Instead, they float in a blurry haze of chance called a superposition until we observe them. The exact second I look through my instruments, reality picks a lane. Old-school astronomy says the wave function, a neat mathematical map of all potential states, just collapses when looked at. But honestly, that explanation leaves me puzzled. What truly counts as an observer, a telescope, a human? Why on earth would the cosmos act differently just because I am watching? To fix this, researchers offered another path. That quantum wave never actually collapses. Instead, every single outcome plays out, just not in our specific sky. They happen elsewhere. We call this the many worlds interpretation. It implies that every single time a tiny particle faces a fork in the road, the entire cosmos splits into parallel realities, living out every option. Picture tossing a coin into deep space. It is both heads and tails until I look. When I finally check the lens, I see heads, but in a branching star system, my exact copy sees tails. Both truths happen, just in separated realities. I am simply grounded on the rock where only one event made history. It sounds entirely wild, I know, but it comes from taking those quantum equations completely seriously. Trusting the math, no extra rules added. The math mapping these stardust particles never demands a single final outcome. They trace the cosmic evolution of every possibility happening together. So why doesn't my telescope spot these other worlds? Why can't we fly a ship right into them? The answer hides in a phenomenon known as quantum decoherence. In these tiny systems, overlapping states ripple and crash, like gravity waves washing across a dark pond. But when these quantum states hit everyday things, like starlight, simple air, or plain heat, that delicate magic simply shatters. Things become classical, solid. The paths lock into separate realities that drift apart, drifting completely out of our observable view. This cosmic split happens faster than a single heartbeat. It is why my telescope never spots moons in two places at once. The cosmos forces a choice so completely that we, stuck in our own reality, only ever see one timeline. Yet you might be wondering, if my telescope cannot ever reach these hidden universes, are they actually real? Is this even hard science without proof? It is a valid question. In astronomy, proof matters, but we also judge ideas by how elegantly they explain the strange things we observe in the sky. The multiverse theory does not invent strange new physics rules. It simply applies standard quantum equations to everything, including us. It offers clean cosmic logic without needing any magical collapse. Though we cannot peer directly into parallel worlds, we can still test whether the astrophysics predicting them holds up across other cosmic observations. Cosmic inflation beautifully predicts how ancient galaxies scattered and how the oldest microwave light fades. Our telescopic data matches those predictions beautifully. String theory remains elusive, but researchers hope it unifies nature's deepest cosmic forces. Similarly, standard quantum mechanics, the very framework spawning these endless multiverses, stands as the most flawless theory we have. It survives every test, quietly powering everyday marvels like lasers, complex computers, and modern medical scanners. We even notice celestial clues hinting that parallel realities might explain the biggest mysteries of our home galaxy. One massive mystery is cosmic fine-tuning. Deep constants like gravity pulling on planets or the weight of electrons feel perfectly tuned just to let stars burn and humans breathe. Shift those numbers even slightly and the cosmos stays cold. But inside a multiverse, this feels natural. With endless universes holding infinite physical laws, of course we evolved in the exact one where starry conditions just happen to be perfect. It is not absolute proof, naturally, but astrophysicists take it seriously because it elegantly solves deep cosmic riddles that otherwise feel like blind luck. So you and I can see this as not fantasy. It organically grows from heavily tested science, from quantum physics expanding space and vibrating strings. We do not need fake forces. We just ask what happens when we trust the universe's most basic physical laws completely. If tiny particles truly map out every single option, and if they permanently separate like distant galaxies, then space itself does not just choose. It replicates entirely. Not ghosts, real, physical, silent branches of spacetime that drift onward using the exact same laws we see tonight. Looking through this lens, parallel worlds are not fiction. It is the purest reading of quantum reality we have. That is why astronomers listen. Chapter 2, Quantum Origins, Schrödinger's famous cat and the multiverse's birth. Let's follow this back together. To understand where these cosmic mirrors start, we must revisit the most beautifully frustrating puzzle in modern science. Schrödinger's famous cat. It sounds playful, a pet locked in a dangerous box, but it exposes the deepest cracks in our quantum understanding. At its heart lies one question. What happens between pure cosmic uncertainty and the second we finally observe the truth? Back in the 1930s, physicist Erwin Schrödinger dreamed up this trap to mock how blindly people accepted early quantum ideas. He pictured locking a cat inside a sealed chamber with a radioactive atom, a sensitive Geiger counter, a glass of poison, and a hammer. If that atom naturally decays, a purely random subatomic coin toss, the counter ticks, breaking the glass, ending the creature. If it stays whole, the cat survives. Quantum theory claims that until we astronomers actually open the lid to check, everything hovers in a blurry superposition, decayed and intact, so in some profoundly eerie way, the animal breathes and lies dead simultaneously. Schrödinger only meant to insult the theory, but he accidentally created our most perfect metaphor for microscopic strangeness. The notion that a large, breathing entity, like an animal or even a star, could exist in two conflicting states is terrifying, yet it drips naturally from the equations governing our universe. Here is the crucial point: the mystery is never the cat itself, but in how we interpret quantum theory's strange rules about measuring and observing the cosmos. The old Copenhagen view of quantum mechanics claims a wave function collapses the second we observe it. That famous cat becomes alive or dead the exact moment we open the box to look. As a scientist, that troubles me. What counts as observing? Does our mind force the collapse? If this vast universe is just quantum systems, who or what actually decides the final outcome? This is where the many worlds idea offers you and me a beautifully elegant alternative. Hugh Everett brought this profound thought to physics in 1957. The wave function simply never collapses. Instead, it flows steadily and predictably, guided deeply by the true rules of quantum physics. Every single outcome plays out. The cosmos splits into quiet, parallel realities. Opening that box doesn't force the grand universe to suddenly choose between a living or a gone cat. Rather, the universe gently divides. On one cosmic branch, you see a living cat. On another branch, it is gone. Both events really happen, and you belong to both. Your own physical state weaves into the cat, sparking parallel experiences across quiet, infinite versions of reality. We astronomers call this quantum branching. It forms the very bedrock of the vast multiverse we study. Forget the movies, these branches never touch or crash back together. They drift apart forever, like endless trails of starlight quietly expanding into the dark. Whenever a tiny quantum event with a few possible paths happens, and this happens constantly in the microscopic deep, our vast universe splits. Now your human thoughts don't actually force the night sky to divide. This vast branching happens purely through quiet, physical collisions out in space. A stray photon striking a molecule, a tiny particle fading, or our lab taking a measurement. As an observer, you just drift along one of those newly formed cosmic branches, the one matching exactly what your own telescope sees. The math behind this is brilliantly clean, no extra rules. The wave function flows forward smoothly. Observing a star is just a basic physical connection, not some deep mystical magic. In that quiet sense, the many worlds idea is actually far simpler than forcing a collapse. It treats us stargazers like any other cluster of matter, bound by the exact same natural laws. Let's look at this together. Think about how it beautifully solves the deep paradoxes that normally haunt our old physics theories. Under the old Copenhagen model, when does that collapse hit? Does it need a human mind? If a star goes supernova in the distant dark and no telescopes look its way, does it shine? The many worlds model gently glides right past those deep traps, because it never relies on our human observation at all. Every single possibility unfolds, every orbit continues, yet this brings a new mystery. If everything happens everywhere, why do I only experience one path? Why do I see a steady, quiet universe tonight, instead of a wild blur of every reality? The secret lies in quantum decoherence. That is how delicate quantum systems lose their unity by bleeding into the vast space around them. When a tiny quantum system, whether a glowing atom or a cat, brushes against passing starlight or cold air, its shifting states lock tightly together with the massive surrounding environment. The blur between those paths fades to silence. The branches become totally independent. Decoherence never destroys the other possibilities, it merely renders them unreachable to us. Once a system loses its coherence, the cosmic interference stops. The quiet realities split there, and from that very second on, they drift along entirely separate orbits. Let's turn back to Schrödinger's famous cat. Before we unseal that cold box, the atom sits in a pure superposition of both broken and whole. Since the heavy poison and the cat are perfectly tied to this event, that entire closed system rests in a delicate superposition. The second we astronomers open the box to look, we get pulled into that strange, entangled web. The final result isn't one single reality winning out. Instead, we branch out. Our observer selves split into infinite versions, each quietly watching a totally different outcome. We can't feel this cosmic branching happen in real time. I only ever experience the view from my specific branch. But quantum math stretched across the entire cosmos promises me those other paths must be out there. They aren't just ghost stories or loose theories. They are real physical outcomes ruled by identical laws. And please understand, claiming this wave function never collapses doesn't mean we scientists are ignoring our own telescope data. Every working theory in quantum mechanics absolutely agrees on the final lab results. The only real argument is what those deep cosmic signals actually mean. So as you and I look up tonight, we can't see the branching. We just infer it from how beautifully the pure math describes our universe. In astrophysics, the many worlds theory is elegant. It completely avoids defining what a measurement even is. Picture a lab test with me, you and I watching a researcher measure an electron's spin. The particle starts suspended in two states, spin up and spin down. But the moment it's measured, this theory says our entire cosmos splits in two. One version of that scientist sees spin up, the other sees spin down. Both observers recall seeing just one result, but the true cosmic picture holds both realities. We can only test this by checking if it matches the standard quantum physics math we already use. That makes our job tough. Right now, our instruments can't tell it apart from the older collapse models. Still, I love its sheer mathematical elegance and crystal clear logic. It needs no weird mechanical tricks. It refuses to treat human observers as the center of everything. It just lets the cosmic math run. Skeptics say if my telescopes can't see the other branches, this is philosophy, not actual empirical science. But supporters argue that rejecting it forces us to invent magical ideas, like wave function collapse. Those old ideas don't fit our known laws of physics. So many worlds isn't a wild guess, it's just a refusal to break the rules to comfort humans. And the weight of this idea ripples far past tiny atomic lab tests. It means every starlight photon absorbed by my lens, every excited molecule, sparks a brand new reality. So the multiverse isn't hidden in deep space. It's breathing right here, silently unfolding all around us, invisible but perhaps totally inevitable. We are also increasingly using quantum computers to probe the very bones of this theoretical framework. These machines won't spot alternate galaxies, but they will force us to face the raw logic of our reality. They work using superpositions and wave interference. These concepts feel totally natural in the many worlds view. As we learn to shape and control this fragile data, we might just change how we picture the whole cosmic reality. You and I might wonder, why does this matter? If we can't see those other branches through a telescope, why even care? The answer sits deep in our physics. Astronomy isn't just about guessing where a comet goes. It's about knowing why the universe hums the way it does. If this theory is true, our sky is merely one sliver of a massive structure. That giant framework, the entire wave function of the cosmos, just glides forward smoothly. It doesn't care if we open an observatory dome or blink, it simply exists. Staring into that thought feels heavy, doesn't it? Not as some mystical poem, but as cold, beautiful physics. To think countless versions of us are out there, splitting like starlight on glass, is profoundly humbling. It means our reality isn't one straight line. It's a deeply woven net of endless cosmic possibilities. But stick with me here, your life is still yours. You aren't adrift in this vast multiverse. You are a real, solid result, bound by the exact same physical rules as everything else. Chapter 3, The Moment You Divide, How Decisions Forge Alternate Versions of You Out There. Down in the quantum dirt, a choice isn't just a metaphor. It is a literal split in space and time, ruled by cold cosmic laws. Our daily lives make us think we walk one single, steady timeline. But the math of the universe whispers a completely different story. It hints that what looks like a single chain of events is truly just one fiber in a massive, branching structure, a grand multiverse of endless chances. To grasp how space splinters, we have to look back at the idea of quantum superposition. Under old classical physics, a system has only one state. A star is either burning or dead. A light is either shining or dark. But down at the quantum floor, things exist in blended states at once. We call these superpositions. A tiny quantum particle can spin two ways at the exact same moment. Until we finally look at it, The act of measuring or just brushing against the outside universe shatters that fragile mixed state for us. But if we embrace the many worlds view like many of my colleagues, that mixed state doesn't actually collapse. Instead, every single option keeps going, sealed off in completely separate branches of the cosmos. That means whenever a tiny quantum choice happens out there, the physical universe itself fractures. Every single ending comes true, just playing out in a totally different cosmic timeline. And crucially, if we stand out here observing the universe, we become part of this branching cosmos. You and I aren't just watching reality split apart, we divide right alongside it. Let us bring this down to Earth. Picture measuring a single photon of starlight caught in a delicate quantum physics experiment. That particle of light hangs in a superposition of both horizontal and vertical states, once you measure it. Quantum theory says there is a 50% chance of finding it horizontal and 50% for vertical. In the old view, we take the measurement and see just one single outcome, say horizontal. The wave function collapses, erasing the other path entirely. But under the many worlds theory, both realities unfold. The cosmos fractures. Down one branch, you observe horizontal. Down the other, you see vertical. Both versions of you exist, each recalling just one result. What I find so beautiful about this is that branching transcends our physics labs. These quantum events blanket everything. The heat of distant stars, radioactive decay, quantum tunneling, even the neurons firing in my head. They all rely on subatomic uncertainty, and if every tiny fluctuation splits the universe, new realities are blooming around us constantly. You might wonder, does this mean every time I pick cereal over toast or walk left instead of right, I spin off another self? Not quite. As an astronomer, I look at the physical mechanics, not the philosophy of human free will. This model maps the branching of physical reality. Still, human thoughts stem from brain activity, and that biological machinery runs on tiny atoms, ions, and chemicals, all of them bound by the very same quantum mechanics governing the stars. So it is entirely possible this infinite branching weaves into our daily decisions. We just cannot feel it happening. My mind feels like a single stream of consciousness flowing smoothly forward through time, but that is merely my limited viewpoint, not the deeper cosmic truth. Every version of me out there on a divergent branch feels completely whole and continuous. They hold tight to their own memories, dreams, and identity. Even while an ocean of other versions, altered by microscopic cosmic events, drift in parallel. Now, one detail of this multiverse model has always fascinated me as a scientist: probability. If every possibility plays out there, why do we see some events more than others? Why do experiments follow strict statistical rules? The secret hides deep within the math of the wave function. The square of any outcome's amplitude sets its physical weight. Not weight like gravity, but a measure of how much quantum material actually fills up that specific reality. When I run these quantum tests over and over again, the volume of branches displaying one result aligns perfectly with the math, meaning, even inside an endless branching cosmos, cold hard statistics still dominate our data. We call this the Born rule. It is an absolute pillar of modern quantum physics. Out in the astrophysics community, there is a constant debate about whether this math emerges naturally from the shape of the branching multiverse, without having to force it in as an extra rule. Some colleagues argue that it grows organically out of rational choices made in the dark, viewed from inside this fractured universe. And these new realities do not require vast new amounts of raw energy or empty space to exist. They simply live woven inside the fabric of the wave function itself, containing every starlit possibility at once. The grand movement of this wave follows strict, unbending mathematical laws. Nothing gets added or destroyed. The entire multiverse just unfurls exactly as those equations demand. Even with its dizzying cosmic scale, the theory remains incredibly elegant. No magic rules, no vanishing realities, no special treatment for human minds. It governs galaxies, telescopes, cats, and single electrons with the exact same laws. It whispers that our massive universe does not just hold uncertainty. It is the embodiment of uncertainty, playing out in totality, we may never catch a glimpse of these ghost branches through a telescope. Decoherence ensures each reality spins outward independently, forever blocked from interfering. The data splitting these worlds gets tangled with the cosmic environment, completely locked away, and nearly impossible to reverse. So what do you and I make of this? The multiverse hides itself on purpose, but the shadows it casts remain real. The absolute perfection of our laboratory tests, the wild potential of quantum computing, and the unbroken math all point us to a beautiful reality, a cosmos where nothing truly ends, it just endlessly diverges. Together, let's explore what this means for time and memory. In a branching multiverse, every copy of you sails onward with a unique past, present, and future. As an astronomer, I see each tiny measurement splitting reality, forging not just a new timeline, but a completely new continuous existence. Memory functions normally within each cosmic branch. You recall making a choice, blind to the alternate paths another you wandered down. This self-consistency is absolutely vital. It crafts the illusion of one unbroken life, even as realities splinter like starlight. No two versions ever collide or overlap. Each holds its own world, its own form, and its own orbit. The strict laws of physics keep these worlds isolated, neatly preventing any cosmic paradox. When I talk to theoretical physicists, they often compare this branching multiverse to massively parallel processing. Think of a cosmic quantum computer processing countless stars at once. Every fate is calculated, yet we only observe one single result. The hidden others exist in separate, distant pathways, completely isolated and beyond our telescopes. Looking deep into cosmology, some of us suspect our universe has a finite quantum state space, a strictly limited number of fundamental cosmic variables. If that holds true, the multiverse might not be truly infinite. Rather, it is vast and deeply complex within a bounded sky. Others disagree entirely. Endlessly splintering branches weaving every possible particle arrangement. That means copies of our Earth, this quiet night, and even you. But what about your identity? If distant versions of you exist out there, are they you? Do they share your mind? The many worlds theory leaves us stargazers guessing on these deep philosophical questions. It treats every timeline as a real, physical place, but ignores the nature of self. Most of my colleagues argue that identity, like the light hitting my lens, is trapped inside one single branch of observation. Still staring into the dark, there is an existential echo. The cosmos doesn't just dream up possibilities, it physically builds them. Every possible event eventually happens, and every version of you that could exist lives out there somewhere. Forget destiny or cosmic fate. This is simply what the raw math of quantum physics reveals when we observe it closely, without any exceptions. That certainly doesn't mean your everyday choices lack meaning. Exactly the opposite. In your personal universe, your actions carve the future. The multiverse never erases your own free will. It simply reframes it. While all cosmic outcomes float out there, you only experience this one, passing like meteors, decision by decision. Your Earth, this exact reality, is vividly, tangibly real. Even with endless parallel branches shining out there, you never need to worry. They aren't lingering ghosts, just separate orbits cutting through a much deeper cosmos. A darkness you blindly cross whenever quantum uncertainty meets physical observation. Chapter 4, the quantum wave function never collapses, changing everything completely. Tonight, you and I are going to explore the wave function, a mathematical object holding all the true data of any quantum system. Whether I'm tracking a lone electron, a photon, or an atom. This mathematical model predicts every possible state a particle might take and its exact odds. It is the beating heart of quantum theory we rely on. It flows smoothly through time, guided by a beautifully established mathematical law. So what happens when I actually measure a star? Standard texts say the wave function simply collapses on the spot. Every encoded possibility vanishes into the dark, leaving only the single flicker of light I observed. That collapse happens instantly. It violently shatters the smooth, graceful evolution of the entire cosmic system. It forces a strange exception, a glitch where universe rules shift just because my telescope happened to be looking. For decades, my peers accepted this sudden collapse as a haunting but necessary piece of quantum theory. The math worked, it matched our lab results with astonishing precision, yet left the biggest celestial questions completely unanswered. What even is an observation? Does the galaxy truly change its shape just because we look? So what do you and I make of this mystery? The many worlds framework steps in to offer a beautifully elegant alternative. Instead of pretending the wave function breaks the moment we observe it, it suggests the wave function never collapses. It just drifts smoothly, eternally, across the entire cosmos. Every potential state keeps shining in the dark. They just aren't all burning inside our specific universe. From my observatory window, a measurement isn't a sudden collapse, it's an interaction. One tiny system dancing with another. When starlight hits my detector or I jot down a result, that quantum system softly entangles with its environment. The wave function doesn't just collapse into one single cosmic outcome. It expands, seeding every possibility into a brand new branch of the cosmos. Let's look at a simple example together. Picture a solitary atom with an equal chance of decaying. Its wave function simply hangs in a quiet superposition, decayed and completely intact. When my observatory tools finally measure that atom, old physics tells us the wave function simply collapses. The atom is decayed or whole, but in the many worlds framework, both cosmic realities actually unfold. The telescope's detector tangles deeply with both states, splitting reality into two branches. One branch sees the decay flash, the other sees darkness. For us physicists, this beautifully fixes the frustrating measurement problem. In the older quantum models, the mere act of observing something was treated like magic. They treated observation as entirely different from natural physics, but to me, that feels completely arbitrary. Why would stardust follow one set of rules in the dark void, only to suddenly change its behavior the very moment my telescope spots it? Eliminating the collapse completely, the many worlds view removes this strange inconsistency. It simply views our measurements as just another ordinary, quiet quantum interaction. No different than two distant stars colliding in space. The wave function just flows forward endlessly and smoothly. No sudden cosmic jumps, no weird pauses, and no special pedestal for us astronomers. The exact same laws govern a speck of dust and the largest gas giant. This beautiful continuity means our reality is entirely quantum. Not classical physics hiding quantum secrets, but purely quantum all the way up. The solid, predictable night sky we map out, with exact planetary positions and fixed events, is just an illusion born of decoherence and human perspective. Our version of reality is just a single glowing thread running through the massively branching cosmic wave function. As a scientist, explaining this is hard because it totally shatters our simple, everyday human intuition. We don't feel the universe dividing around us. We don't see stars glowing in two places at once. We just live out one single timeline. Yet the math elegantly accounts for this too. Once an interaction takes place and decoherence steps in, these cosmic branches permanently stop interfering with each other. Each separated branch holds an astronomer looking through a telescope, seeing only their specific night sky. You and I can't interact with these parallel worlds. We can't jump across galaxies or whisper to our other selves. Decoherence forces each universe to evolve alone, and the data that sparked the split simply vanishes into the cold cosmic background. The branches are real, incredibly distant, and still deeply controversial. The sheer scale upsets my colleagues. If every quantum flicker creates a new split, the number of parallel realities dwarfs the observable stars. Critics call it a wildly extravagant idea, endlessly multiplying universes far beyond necessity. But I argue it avoids complexity. It simply deletes entirely arbitrary rules. Instead of forcing a collapse, we just follow the elegant math, and the math predicts a beautifully branching cosmos. The Schrödinger equation, the very heartbeat of quantum evolution, has absolutely no natural mechanism for collapse. It maps out smooth, flowing movement. Whenever physicists try forcing a collapse, they have to patch it in by hand without any natural underlying physics. That makes the collapse idea feel like strange magic, deeply clashing with the rest of our theories. Some researchers have tried building models to explain the collapse using completely new physics, like spontaneous gravity theories and objective reduction. These ideas try to frame wave collapse as a genuine, observable physical event. But our telescopes and labs haven't proved them yet, and many struggle badly to align with observed quantum behavior. The many worlds view, however, needs no artificial additions. It trusts that the wave function alone captures the entire truth of reality, and that the universe flows forever according to one single, beautifully unchanged equation. The universe doesn't change its cosmic nature just because my telescope watches it. It just stays quantum. I find that deeply, quietly appealing. It unites quantum space with cosmic gravity, letting physical laws stay beautifully universal. It completely bypasses the awkward headache of strictly defining observers and lenses. And it opens our observatory domes to a far richer grasp of existence. A cosmos that feels deeper and entirely complete. Let's ponder together what this actually means. If this quantum wave never dies, then our present moment is merely a thin, glowing sliver of a massive cosmic structure. Every spark of starlight or shadowed outcome that could have existed in the past remains alive today. They aren't just empty possibilities, but entirely real universes expanding outward into the infinite dark. When you and I look up, every cosmic outcome exists, waiting to unfold in some version of reality. This doesn't mean our universe is purely chaotic or that anything goes. The laws governing the stars apply with perfect mathematical precision, covering all outcomes, not just the one we see. Reality isn't a straight line. Think of it as a vast, branching tree. You live one specific path. Your memories and experiences are entirely real within your branch. You never feel the universe splitting, and you shouldn't. From our earthly vantage point, events unfold logically, but the deeper cosmic truth is much more complex. Beneath the surface of our night sky lies a quantum structure of staggering scale. Let's also look at the hard experimental support. We can't directly test these many worlds yet, since our telescopes can't pierce the veil of other branches. Yet it matches the predictions of standard quantum mechanics in every single experiment we run. Its true advantage lies in theoretical simplicity and philosophical elegance. By trusting quantum mathematics entirely, the many worlds view avoids clunky inconsistencies and unexplained physical rules. Also, modern quantum computing adds massive weight to this. Famous algorithms actively use interference between different computational branches. While these processing branches do not perfectly match alternate universes, the overlap forces us astrophysicists to rethink how quantum math mirrors parallel realities. The idea that countless calculations are carried out invisibly, all at once, aligns beautifully with the notion that many distinct realities unfold in parallel. This doesn't mean our machines prove the multiverse, but they highlight how intuitive quantum mechanics gets when we accept the wave function as continuous and real. It isn't something to ignore. It must be understood as the fundamental structure of all physical nature. As astrophysics progresses, we keep exploring other models, from hidden variables to objective collapse theories. But no actual evidence has ever disqualified the many worlds view. I see its mathematical purity as a guiding star. It may not be the final answer, but it remains deeply consistent with the quantum world we observe. And that brings us to the quiet revolution. Reality might never collapse. We might not be trapped on a single thread of possibility. You stand on Earth following one path, while countless unseen others unfold, governed by the same elegant physics. Your life is not diminished by this vastness, it is enhanced. The math doesn't erase your story. It simply places you within a wider cosmos, a universe that preserves possibilities instead of destroying them. In a galaxy where the wave function never collapses, nothing is truly lost. Every outcome has a place out there in the dark, and in the calm stillness of an observatory, there is something profound. Even the tiniest stardust particle obeys laws that leave room for absolutely everything. Chapter 5, Quantum Decoherence, Why the Other Universes Stay Hidden. If space really branches every time a quantum event has multiple outcomes, a very natural question arises. You and I have to ask, why don't we see these branches through our telescopes? Why just one outcome? The answer hides in a crucial concept of quantum mechanics known as decoherence. This effect perfectly explains how the classical world we physically observe emerges from the strange quantum reality. It also gives a compelling reason why the other branches of the multiverse stay hidden from view. To understand decoherence, let's first revisit how tiny quantum systems actually behave. At the microscopic scale, electrons, atoms, and photons don't have fixed positions or velocities. Instead, they exist in superpositions, a blur of all possible states. These superpositions allow strange phenomena like entanglement, but these effects are fragile when a system is isolated. Shielded from the wider galaxy, it maintains coherence, meaning the parts of its wave function keep interfering with each other, but true isolation is practically impossible. Quantum systems constantly interact with their environments. They bump into stray starlight, air molecules, thermal vibrations, or even the lenses you and I look through. These tiny interactions entangle a quantum system with its surroundings. Like starlight blending into the night, its wave function merges into a vast, universal wave function, including the whole environment. When this happens, that original fragile superposition stops acting like one unified, single state. Instead, those separate superposition components evolve entirely on their own, unable to interfere. We call this decoherence, and importantly, this is not a sudden wave function collapse. It never destroys those branches or forces a single outcome. Rather, it just stops these diverging cosmic paths from ever interacting or touching one another again. To an astronomer like me looking out from just one branch, it looks like only a single reality ever happened. But if we zoom out to the universal wave function, all outcomes still exist, just isolated in the dark. Let's look at this together with a simple, grounded example. Imagine a lone particle drifting through space in a superposition, traveling both left and right, if kept perfectly isolated. We could run an experiment to see interference, a beautiful pattern born when the different components of its wave function overlap. But the moment that particle interacts with the universe, say a single photon from a distant star strikes it, coherence vanishes. The universe now knows the particle's path, even without my telescope measuring it. The pattern just fades away. From our earthly viewpoint, it looks like that particle chose one clear path. Yet the true quantum reality holds both paths, forever entangled with the wider cosmos. In the many worlds multiverse, this quiet loss of interference marks a literal branching event. One universe branch holds the particle drifting left, another distinct reality holds it drifting right. Everything around it, from my observatory equipment to me myself, becomes entangled with that outcome. Each cosmic branch grows completely alone. Interference fades because that crucial data scatters across the vast vacuum of space, far beyond our reach. This very entanglement is exactly why we never see strange quantum states in daily life. Heavy, everyday objects like telescopes, planets, or even us astronomers are built from billions of particles, constantly colliding with the surrounding galaxy. Any quantum superposition involving huge objects decoheres in an instant. That coherence window where interference might happen is incredibly brief. So while the universe constantly branches into new superpositions, we only ever feel one reality. Decoherence builds a quiet bridge between quantum mechanics and classical physics. It explains how the weird, hazy laws of atomic space create the solid, reliable universe we observe every single night. It's not that quantum mechanics suddenly stops working. It is just that quantum weirdness gets hidden, buried inside complex webs of cosmic entanglement. The most beautiful part is we can actually test this. In our labs, researchers have measured decoherence across tiny systems like trapped ions, cold molecules, and superconducting quantum bits. Inside freezing, perfectly shielded vacuums, we keep that delicate coherence alive just long enough to study it. But the absolute tiniest cosmic disturbance, a rogue photon or a tiny heat wave, shatters that state. These observations match our deepest theoretical math perfectly. Lately, this profound understanding has become the absolute heartbeat of modern quantum computing research. Those machines depend entirely on keeping a long, stable coherence between quantum bits for complex math. Decoherence is their worst nightmare. If those sensitive qubits brush against the outside universe even slightly, that delicate quantum data disappears, crashing the entire calculation. This intense hurdle has pushed science to invent clever tricks like quantum error correction and extreme isolation, trying to shield those fragile states from the universe and stretch coherence out as long as physically possible. Now you and I might wonder about those hidden multiverse branches. Decoherence explains why we cannot see them, but proves they are never truly destroyed. They remain fully real inside the cosmos' total wave function. The information is never lost. It just tangles with distant cosmic variables that our instruments can no longer reach. Looking at the absolute largest scale, the universe holds every outcome. It is only that the parallel realities simply stopped speaking to one another. Remember, this fading coherence alone does not actually pick a single winning outcome. It only explains why these starry paths split apart, not why we wake up on this specific timeline. In the many worlds theory, it is just a trick of perspective. An astronomer becomes part of the entangled sky, their mind riding along one branch, completely blind to the ghost realities floating right beside them. Every single version of us sees their night sky as unique, yet every version truly exists. Some peers argue that decoherence, while profoundly powerful, that doesn't fully solve the measurement problem. After all, to observers, the outcome still looks completely definite. But in the many worlds view, this isn't an issue, it's an expected feature. This definite reality simply arises from cosmic entanglement and our unique perspective. We don't need to collapse the quantum wave function to explain the cosmos. What we observe is just one slice of a vastly larger branching universe. To appreciate how deeply decoherence governs our entire cosmic experience, consider that even your thoughts, driven by neural activity, are shaped by microscopic quantum events, much like starlight. But because your brain is a warm, active place full of environmental chaos, this quantum decoherence acts incredibly fast. Every neural signal and firing synapse is completely bathed in countless interactions with surrounding particles, like cosmic dust colliding. The delicate coherence needed for quantum interference vanishes almost instantly. In this way, decoherence shapes both the external galaxies we observe and the very boundaries of our own internal waking experience. It acts as the filter turning swirling quantum potential into classical, solid actuality. That is why you feel grounded in one single timeline, even as our physics suggests that countless parallel cosmic histories are unfolding. Interestingly, fellow scientists continue exploring if traces of this decoherence can be spotted on much larger visible scales. In lab settings, delicate Schrödinger cat states, or superpositions of large systems, have been created using tiny mirrors, complex molecules, and quantum circuits. These tests show how fast decoherence happens and how long quantum behavior survives. Naturally, just like warm planets, larger, hotter systems destroy coherence much faster. This beautifully supports the theory that our classical reality is emergent, not fundamental. So in this grand cosmic picture, the classical world isn't fundamental, it simply emerges. It's a pure consequence of cosmic scale, vast complexity, and overwhelming environmental particle interactions. Decoherence explains why the stars look sharp, even when beneath them lies a deep, hidden blur of endless quantum possibility. Some theoretical physicists suggest decoherence might even drive the arrow of time itself, explaining why we remember past supernovas, but not future ones. As particles grow more entangled with the universe around them, they lose delicate information that could otherwise be reversed. Cosmic entropy climbs, creating that sense of forward time. It's a speculative idea, but it truly illustrates decoherence's massive reach. It touches not just how we perceive deep space and matter, but the very flow of time itself. Perhaps the most profound cosmic implication is that the multiverse isn't hiding. It's just shielded by the exact same mechanism that makes our own reality feel coherent. We never see the universe split because those parallel branches are sealed off by decoherence. We won't ever meet alternative versions of ourselves because we have fully decohered from them. They aren't destroyed, just separated by a boundary deeper than intergalactic space, the vast boundary of quantum entanglement and complexity. So as you and I go about our day, watching starlight scatter across the trees, listening to echoes or feeling the weight of your memories, it's all filtered through this decoherence. You aren't just a passive observer standing under a singular night sky. You are a coherent observer, riding along one thread of a sprawling, branching universe. And while our telescopes may never see the others, quantum physics promises they exist out there, silent, parallel, and totally real. Chapter 6, Branching at the Microscopic Scale. How often does our massive universe actually split? When folks first hear about the multiverse inside quantum mechanics, they usually picture our universe fracturing only during huge, earth-shattering events. The flip of a coin, a telescope measurement in an observatory, or some massive, life-changing choice. But quantum mechanics doesn't just operate on a human scale of perception. It governs absolutely everything, from microscopic dust to the largest galaxy clusters in the cosmos. To grasp the multiverse's true scope, you and I must look way past everyday events, zooming into where cosmic branching really happens. It turns out this universe doesn't just split during rare astronomical moments. It fractures constantly, at microscopic scales that completely defy our imagination. At the very bedrock of this cosmic idea is that quantum interactions are purely probabilistic. Orbiting electrons lack precise positions or paths. Light photons don't fly in perfectly clean lines. Instead, particles blur into superpositions, holding multiple outcomes. And when they collide with other matter, those superpositions evolve, fracture, and become deeply entangled. In the many worlds theory, every single tiny interaction creates a branching universe. Let's look at a remarkably simple example. A single photon of light hitting a semi-transparent observatory mirror. There's a 50% chance that starlight reflects and 50% it passes through. In classical physics, we'd say it simply takes one path or the other. Look closely with me. In quantum mechanics, until we detect a photon, it rests in a superposition of both outcomes. And when that light hits our telescope sensors, the whole setup, the mirror, the photon, and the sensor itself, falls into an entangled superposition. In the many worlds theory, reality branches here. One path holds a universe where that ancient starlight reflected. Another holds the universe where it slipped right through. Every outcome becomes real in its own isolated branch of existence, floating onward forever. To us, this is not just math. Quantum electrodynamics is the most perfectly tested theory we have. It is built entirely on these superpositions and microscopic interactions. Every time charged particles meet, every photon our instruments absorb, every quiet flutter in the vacuum of space is ruled by pure probability and wave functions. Which means, theoretically, the universe is fracturing on scales of space and time too small for our lenses to see. So how often does the cosmos actually divide? Well, it depends on how closely we decide to look. If a split happens with every interaction causing decoherence and entanglement, then reality is tearing into new branches constantly. Every single second, every point in deep space, each quantum spark spins off new, silent branches. Think of the air inside my observatory. It is packed with countless gas molecules endlessly bouncing, colliding, and trading heat. Zoom in and every single collision is a tiny quantum event. Each crash could spark a massive web of potential. Outcomes carrying slightly different flight paths, speeds, or precise scattering angles. Every tiny shift sparks another possible split, tightly binding the surrounding environment to that specific, fleeting result. And since these microscopic clashes happen billions or even trillions of times every single second, even in a tiny pocket of empty space, the sheer number of new timelines explodes. Honestly, the sheer volume of alternative histories born from these tiny impacts grows exponentially as time marches on. We are left with an unimaginable swarm of distinct paths, each holding a slightly altered version of reality. But that does not mean every wild possibility occurs with the same rhythm or equal weight in the math. Our quantum models give a specific amplitude to each result, which perfectly sets their odds. Most paths carry a tiny amplitude, meaning an observer like me has almost zero chance of seeing them. Yet, they remain baked into the structure of the wave function. And through the lens of the many worlds theory, those faint paths are utterly real. Crucially, not every single split creates a wildly unrecognizable cosmos. Many of these dark branches change by the smallest whispers, the quiet spin of one electron, the lonely drift of a single photon, the hum of one molecule. Most of these new realities stay almost identical to ours, at least for a little while. It is only as millennia pass and these microscopic shifts compound that timelines slowly drift into totally foreign histories. This cosmic math leads to a rather stunning realization. Picture this with me: most of the multiverse might be packed with universes almost exactly like ours. In one, a cosmic ray strikes an atom in your brain a nanosecond earlier. In another, stardust settles half a micron to the left on a telescope lens. These sound like meaningless shifts, but they remind us that the cosmos isn't forged from solid, fixed events. It is an endless, flowing web of interaction. We actually see this branching play out clearly when we run controlled quantum physics experiments. In laboratories worldwide, my colleagues and I use beam splitters and trapped particles to map out the sheer probability of existence. These delicate tests show us exactly how superpositions and branching happen right down at the individual particle level. When we place or remove our sensors, the final data shifts, not because the starlight made a choice, but because the quantum state evolves based entirely on how we chose to observe it. Inside these dark rooms, the blur of quantum uncertainty doesn't suddenly collapse into a classical fact. It simply entangles with something larger, our heavy instruments, the chilly room, and finally us. Every single time we look, reality fractures. And since our modern telescopes process millions of ancient particles at once, the count of new universes explodes. Still, I have to stress, these new branches aren't neatly stacked like telescope lenses, nor are they floating through physical space like parallel worlds from an old science fiction movie. They are pure, mathematical shapes of the wave function. Silent paths bound by the exact same math, and once that final split happens, you and I can never send a message across the void. My fellow physicists and I often try calculating just how many branches emerge after a mere fraction of a second. Those numbers shift depending on the interaction scales and coherence limits we model, or the sheer size of the system, but the final count is always staggeringly huge. In just a few seconds, a simple speck of cosmic dust catching starlight can split into more distinct quantum histories than there are actual atoms in our entire observable universe. But looking at this multiverse, I don't see chaos or disorder. Far from it, this vast branching strictly obeys the elegant mathematics of quantum mechanics. It flows smoothly, guided by strict wave amplitudes. Each new timeline simply emerges from the last. I see no leaps or cosmic paradoxes here. The wave function simply evolves, like a deep river splitting into endless tributaries. Every path remains consistent, every outcome unfolds naturally. As these cosmic branches multiply, the grand architecture of the multiverse grows deeply rich. Some paths forge radically different worlds. A single decaying atomic nucleus might trigger a cascade of events that entirely rewrites cosmic history. Other parallel realities might seem nearly identical to their neighbors. Yet all stem from one beautiful process, a continuous, unitary evolution with no sudden collapse. You and I might wonder what this means for us, not just as stargazers, but as active participants in this branching cosmos. It means that as a conscious being, you are endlessly entangling yourself with the very physical universe around you. Whenever you observe a star, make a choice, or form a thought, driven by those tiny physical interactions, you anchor into a specific quantum timeline, and the version of you in another branch simply made a slightly different choice. Maybe they looked away from the telescope, spoke instead of staying quiet, took a step that sparked a totally different path through the cosmos. You will never meet these alternate selves. Quantum decoherence has sealed those realities away from our instruments forever, but they remain. Woven right into the fabric of the universal wave function, not fictional, not just imaginary. Just kept apart by the endless branching flow of quantum mechanics, which brings us to a quiet realization. The cosmos doesn't split with dramatic supernovas or massive flashes. It fractures softly, billions of times a second, down at subatomic scales we could never hope to feel. And yet those delicate branches hold absolutely everything, every outcome, every variation. Every single possibility that physics allows. You are woven into this vast system, not just watching from an observatory, but living it. Every breath and upward glance feeds the branching. Your life, much like the life cycle of a star, is just one thread in a massively dividing structure. And while you will never sense those other realities, the exact same physical laws that shaped our sky shaped theirs. From my perspective, reality isn't just one lonely film strip playing out in a single direction. It is a massive cosmic archive of possibilities, endlessly expanding outward, written by quantum logic instead of simple fate. And right now you're sitting in that archive reading a single page. Turn it and another cosmic branch begins. Chapter 7, Does Probability Still Hold True Across a Sprawling Multiverse? Down here on Earth, probability is a comforting tool. We use it to predict tomorrow's weather, the odds of a simple game, or where a photon might land in our telescope sensors. In classical physics, probability just reflects ignorance. It highlights our lack of exact data about a system. If we astronomers knew the exact position and velocity of every particle out there, we could theoretically predict the entire future. But when studying quantum mechanics, probability is something far deeper. Even when we perfectly map a system's wave function, the mathematical core holding all potential outcomes, we still can't predict one single, solid result. Instead, we are left with a spectrum of probabilities. An electron could appear here or perhaps over there, but never with absolute certainty. Even when we set up the exact same experiment and measure it repeatedly, the data scatters. We can only assign likelihoods. This framework actually works beautifully in standard quantum mechanics. But within the many worlds interpretation, a new puzzle arises. Let's think about this together. If all outcomes happen across different branches of the multiverse, what does it even mean to talk about probability anymore? Probability naturally assumes only one single event occurs while the rest fail. You roll a 6-sided die and simply get a 4. The chance of rolling a 6 was real but vanished. Yet in a many worlds model, every single face of that die is rolled. Every statistical outcome plays out perfectly inside its own isolated timeline. If the cosmos excludes absolutely nothing, what purpose does probability serve? Looking at the math, you might think the concept completely loses its meaning here. If the universe forces every potential outcome into reality, does it still make sense to call one event more likely than the other? We have to ask together, why should the frequencies we actually observe match the probabilities calculated by the Born rule? The rule telling us to square a wave function's amplitude just to map out its hidden probability. Surprisingly, yes, but to see why, you and I must look deeper into what chance means inside a branching universe. In classical physics, probabilities simply represent missing information. They show a lack of knowledge, but in quantum mechanics, and especially in the multiverse, chance becomes physical. It reflects the very architecture of reality itself. In a branching cosmos, we aren't talking about ignorance of what will happen. We are observing the physical distribution of weight across different branches. It measures how heavily different outcomes unfold within the evolving wave function. And this weight is never just a simple count of branches. The cosmos holds infinite branches, and even the faintest shift creates new ones. Instead, it ties directly back to the squared amplitude of that wave. That number tells us exactly how much of reality belongs to a single branch. Through our telescopes, we see not all branches are equal. Some carry far more cosmic weight. And that weight becomes the probability that we, as stargazing observers, will wake up in one universe instead of another. This creates a quiet but deeply important distinction. If we view the total wave function from the outside, every branch is completely real. But from the inside, living deeply embedded within that infinite wave. The experience of any single outcome holds a probability, one that perfectly matches the relative amplitude of the starry branch they call home. To put it simply, probability out in the multiverse does not mean we are uncertain about what happens. It means we are uncertain about which cosmic branch we inhabit. You know all possibilities unfold out there, but you cannot know beforehand which version of yourself will witness which event. Before looking through the lens, you are one unified observer. Afterward, there are many versions of you, each holding a true record of one event. This might sound strange, but it aligns perfectly with observation. When we run a quantum experiment, like measuring the spin of a distant particle, we only ever perceive a single result. We see light, not dark, and when we run the test night after night, our observations perfectly match the probabilities predicted by the Born rule. Even though every outcome happens, the frequencies we witness follow a beautiful pattern. Let's look closely at where quantum decision theory and pure rationality come into play. Many of my fellow physicists have tried to prove that if we embrace the logic of the many worlds theory, we naturally recover the Born rule. The beating heart of quantum probability, as a simple consequence of rational observers who understand they are drifting through a branching universe. Some of the brightest work in this area comes from David Deutsch, with elegant later refinements by David Wallace. Their models rely on decision theory, the exact same logic that guides economics and pure probability, to ask, what choices should a rational mind make, living in a cosmos where every outcome happens, but with varying cosmic weights? Their answer is that a clear-minded observer must weigh those outcomes by the square of the wave's amplitude, just as the Born rule dictates, if they want their choices to stay consistent across the endless starry branches. From this cosmic vantage point, probability becomes a telescope for predicting our future location in the multiverse, not a measure of what is physically real. Crucially, this view keeps our theories perfectly aligned with actual laboratory results. If we run an observation thousands of times, the patterns seen by every version of you across the night sky will cluster around the Born rule. The sheer volume of scientists witnessing those normal patterns completely drowns out anyone seeing strange anomalies. So what do you and I make of this? The law of large numbers holds not in one branch, but across the entire cosmos. This has led some of us watching the skies to suggest that probability is a beautiful, emergent property. It is not a rigid law handed down from the stars, but a purely statistical rhythm that naturally grows from the branching void and the gentle evolution of the wave. Just as heat rises from moving atoms, quantum probability blooms from the very architecture of the multiverse. There is another quiet layer here, the deep mystery of self-locating uncertainty. Before looking through the glass, you know every possibility will happen, but you cannot know which version of yourself you will wake up as. This brings in a kind of chance that isn't about stellar physics, but about human identity. Which future version of myself will I be? Even in a deterministic cosmic model like many worlds, this subtle uncertainty lingers, keeping probability as a deeply meaningful idea when we observe and decide. You and I might ask, can this cosmic theory ever be tested? Can we truly observe a difference between collapsing reality and branching universes? Sadly, no instrument in our observatories today can finally answer that. Both cosmic models predict the exact same physics, yet what the multiverse lacks in direct visibility, it balances with beautiful, sweeping mathematical harmony. And so our debate goes on. Some colleagues argue without a hard collapse, chance loses meaning. Others feel probability simply finds a far more natural, elegant foundation. It all comes down to what we expect from the cosmos. A clockwork cosmos with internal odds or sudden collapse and true randomness. The many worlds theory remains beautifully deterministic. It never erases mystery from our lives. It simply reframes our view from a much wider cosmic perspective. This holds strange yet gorgeous implications. It implies your journey under the stars isn't random, but unfolds through a profound mathematical structure. Experiencing this reality instead of another isn't because the rest failed to spark, but because you are simply this unique observer. Other valid, perfectly structured realms drift away like distant galaxies. You aren't alone in the multiverse, yet you remain entirely singular here. The odds we calculate for tomorrow are never just guesses. They reflect where cosmic mathematics predict our awareness will likely travel next. Every single quiet moment we live carries a sprawling web of branches, all endlessly real and evolving. We orbit one path with chances guided not by fate, but by the weight of a wave function. So yes, out here in the multiverse, probability survives. It is never diminished, only beautifully redefined. not erased, just illuminated. We still roll the cosmic dice, we still choose, and we still hope. And through all of this, the branching cosmos follows its ancient rules, splitting so gently, silently, and endlessly all around you. Chapter 8: Why we can never cross the multiverse to speak or travel. Let's shift our gaze. The multiverse sparks our imagination far beyond stellar physics. Science fiction loves voyagers crossing between parallel universes, beaming signals across timelines, or consciously steering into alternate realities. It is a breathtaking story, treating the vast multiverse like a simple star chart we could plot and sail across. But quantum mechanics, even while predicting this infinite ocean of worlds, heavily locks the observatory doors on those wild dreams. As I study the math, reality fractures continuously and universally. But once timelines split, they enter cosmic isolation. No starlight, signal, or energy can ever bridge that silent void. In the truest sense, these parallel night skies aren't merely distant. They remain forever unreachable, deeply severed by the very nature of quantum evolution. To see why, we must point our lens toward a phenomenon known as quantum decoherence. As we mapped out earlier, decoherence happens when delicate quantum systems brush against their environment, losing their ability to beautifully overlap. When a tiny particle, perhaps a lone photon, tangles with its surroundings, its possible paths bloom into separate cosmic branches. These mimic different physical events, like starlight slipping through a gap or striking a heavy lens. Once decoherence settles in, those alternate paths can never again touch or ripple across one another. After this shift, the branches break away from being one unified, harmonious quantum system. They remain pieces of the grand universal wave, true, but their physical interactions are completely silenced. That silence is absolute. On paper, these divergent worlds still share a mathematical bond within the majestic, complete quantum state. But through my lens, the sheer quantum data separating them scatters into the void. It vanishes so deeply that no astronomer or gleaming instrument could ever rebuild it. In cosmic physics, information survives. The grand wave's evolution remains beautifully whole and mathematically reversible. But we cannot rewind decoherence. The exact data distinguishing one stellar branch from another still survives out there. Yet it is hopelessly smeared across the dark expanse, scattered like dust among photons, gas clouds, and passing atoms. Gathering that scattered starlight means forcing the entire surrounding universe back into one perfectly synchronized quantum alignment. An unbelievably delicate task demanding we control every single tiny vibration since the very moment the cosmos split. Because of this harsh reality, we cannot radio another branch. So as we watch the sky, know we can't build ships to meet alternate selves or chase those phantom outcomes. As an astronomer, I know these ideas are not just technologically impossible. Physical laws forbid them. Once decoherence strikes, branches are locked in their own cosmic paths, unable to cross or swap signals. I know that sounds disappointing. If this vast multiverse is real and countless versions of us exist out there, you and I might wonder, why can't we reach them? Why can't we learn from their science or see their histories? The secret hides in what these branches truly are. We aren't talking about physical galaxies, nor parallel timelines floating side by side in some higher dimension. They are isolated mathematical pieces of one massive, beautiful structure we call the universal wave function. They do not sit next to each other in deep space. There is no cosmic wormhole or magic bridge between them. The gap isn't physical space, it's pure information, and quantum data is fragile. You cannot clone it perfectly, nor can you blast it across the stars faster than light. These strict physical laws rule our own cosmic branch, and they double as absolute barriers between the other universes. Even if we built massive quantum computers to bend wave functions across galaxies, we would still hit the cold wall of decoherence. Our vast universe never erases its history. It just keeps realities from crashing together. Consider a common myth. The famous idea that quantum entanglement lets us talk to other universes. Quantum entanglement is a stunning, very real physical phenomenon. Two particles link so deeply that observing one instantly sets the other, even if they are light years apart across the cosmos. But this bizarre effect cannot actually be used to beam messages. It is purely statistical, bound by strict quantum laws, and crucially, entanglement only happens within our single branch. Once a universe splits, those systems break contact. Entanglement cannot leap across the void. So if we can't travel or send signals out there, what is left of the multiverse? Is it just unreachable starlight? Not quite. The multiverse isn't a place to visit, it is an explanation. It helps astronomers understand exactly why quantum mechanics behaves this way, and why probabilities follow strict mathematical rules. Why cosmic decoherence creates normal reality, and why our telescopes see what they do. Through my telescope, the multiverse isn't a playground, it is the very bedrock holding our cosmos up. It contains all possible stellar histories and outcomes. You don't need a spaceship to reach it, you're already living inside its branches. Molded by shifting cosmic fields, distant particles, and endless webs of entanglement. Guided by wave logic and the elegant math of the Schrödinger equation. To see why jumping branches is scientifically impossible, look at reversibility. On paper, quantum systems can rewind perfectly. But out in space, reversing a universe that has split apart would mean perfectly tracking down every single scattered particle that ever bumped into your system. You would need every drifting photon, every wisp of stardust, the whole quantum fingerprint of a huge slice of space. This isn't just hard, it is strictly forbidden by the laws of physics. Honestly, if you could rewind it all, you would shatter the arrow of time itself. Entropy constantly increases, driving our stars from past to future, because quantum decoherence simply cannot go backward. If you tried to unbranch the whole cosmos, you would have to flip thermodynamics and force the entire universe to march in reverse. Physics will never let us take that path. Even if my team could pull off a miracle and fuse branches, you wouldn't get to meet your parallel self. You would just create a messy quantum interference pattern, blending pieces of space that were once separate. You wouldn't have a deep conversation, you'd just see a strange statistical blip on our lab monitors. Space is not a movie we can rewind, nor a map we can sail across. It is an ongoing evolution, locked into consistency and the forward flow of time. These firm limits don't come from a lack of human imagination, they are built right into quantum theory. The same elegant rules that allow the wave function to bloom and branch also lock those worlds apart forever. We cannot smash these walls. The universe wrote these firm limits into its own math, but as you and I can see, the multiverse remains profoundly meaningful. Honestly, that distance, that absolute unreachable void, is exactly what draws us in. Just because we cannot signal these parallel worlds or bridge the cosmic gaps between them doesn't erase their reality. We are simply bound by the quiet laws of physics. Our universe is just one long, glowing thread woven through a much vaster cosmic dark. As we scan the heavens, it makes you pause. What does it actually mean that endless versions of you exist? Living out entirely different lives, taking other paths, completely cut off from the one you know. It means your universe, as lonely as it sometimes feels, belongs to a massive, perfectly ordered whole. You don't need to touch those distant realities. Knowing they exist gives profound meaning to yours. Every breath you take here is born from those silent splits in reality. To an astronomer, the multiverse isn't some distant map waiting to be conquered. It reminds us to just sit quietly and look inward, marveling at the sheer, beautiful chance of your own existence in this endless cosmic branching. You are not trapped in a single timeline. You are the timeline, you aren't missing out on the rest of the cosmos. You are living one beautiful life under the same physical laws that allow the rest to exist in the dark. So no, we won't be building starships to cross the multiverse. But it still shapes your world, your gravity, your steady march through time. It all flows directly from that endless, unseen splitting of worlds. Looking through the telescope, every small choice holds a strange cosmic weight. They lock in the single orbit you will follow forever. Chapter 9, you and I need to ask, can we actually test this many worlds idea? This quantum theory paints a stunning, infinite picture of our reality. A cosmos endlessly fracturing into quiet, hidden copies. Storing every single possibility, it perfectly fixes the math problem without needing reality to suddenly collapse. making the quantum wave entirely real. It glides smoothly alongside the strict laws of physics. Yet for all that beautiful starlight elegance, the theory hits a massive wall. Can we actually prove it? Can astronomers stuck on one tiny rock in one lonely timeline ever gather the hard data to prove or deny the billions of unseen worlds? This exact problem strikes right at the core of what makes any science real or just a dream. When we study the universe, we demand our theories make firm predictions. They have to risk failing. That simple rule is what separates true astrophysics from pure imagination. So does many worlds pass the test? At first glance into the lens, no. Every quantum theory, collapsing or endlessly branching, gives us the exact same data when we measure a star or an atom. Whether reality shrinks down to one choice or fractures into a million hidden skies, our lab instruments will click and flash in the exact same pattern. As long as these theories match our telescope data perfectly, it feels impossible to pick a clear winner from here on Earth. But the deep space reality is much softer than that. It is entirely true that many worlds offers identical numbers for our daily experiments. But it forces us to accept a radically different universe, a different structure of existence entirely, and that alone leaves room for some quiet, clever testing. We might not see the starlight from those parallel skies, but we can ask if assuming they exist makes our own universe make more sense, or if the older theories are just too messy. This is where simplicity shines like a clear night sky. Many worlds add zero extra rules, no strange triggers for reality collapsing, and no special pedestals for the astronomer observing it. It treats every particle exactly the same, following one smooth, unbroken mathematical flow. Meanwhile, the old collapse theories have to declare exactly when that collapse strikes. What counts as looking, and how random chance creates one solid reality. Those extra rules feel clunky to us physicists, disconnected from the raw physics. On that front, many worlds is beautiful. It explains the exact same cosmos, but assumes much less. That clean elegance has deep power. It is our simple way of letting the pure mathematics show us the hidden truth. And stargazers always prefer a simpler map. You and I can also see this play out by looking at how these ideas spark entirely new science. Lately, researchers are deeply curious if that quantum collapse is a hard, physical event. This inspired new objective collapse models, like the GRW theory, or Roger Penrose's beautiful idea involving gravity pulling reality together. These suggest the collapsing quantum wave isn't just chalkboard math, but a real, physical shockwave we can actually measure. An event that sparks on its own, drifting in the dark without anyone looking. And models like that make faint, distant predictions that actually differ from standard physics. Out in the cosmos, these deviations are testable. Just as we scan the sky for faint signals, physicists search for spontaneous collapse, hunting for unexplained heat or tiny, random stutters in particle motion. So far, we haven't seen a single deviation from standard quantum rules. Even when testing large superpositions, like Schrödinger's cat states in superchilled circuits, there is absolutely no sign of collapse. These systems just flow. They follow unitary dynamics, fading naturally without needing any sort of sudden reduction. These findings aren't direct proof of the many worlds interpretation, but they slowly chip away at the alternatives. Our next frontier is quantum computing. Algorithms like Shor's and Grover's are specifically built to ride on superposition and interference. For many stargazers and theorists, this immense computing power makes sense under many worlds, where every single computational path actually happens across different branching realities. Look at it this way, a quantum computer isn't working inside one lonely world. It calculates across a vast, endless branching multiverse. While this view remains an interpretation, it aligns beautifully with the math, yet many worlds faces a massive hurdle. Its main idea, those other branches, remains completely hidden from our telescopes. By design, these parallel branches are decohered. They never cross. They leave no trace in our night sky, making experimental proof incredibly difficult for us. To fix this, some thinkers propose clever thought experiments centered around quantum revival. In theory, if we perfectly isolated a quantum system and reversed its decoherence, we might actually bring those lost, disconnected branches back into contact with ours. This would create a ripple between histories, a faint echo whispering from another universe. But honestly, pulling off an experiment like that is far beyond any lab on Earth today. Shielding a system from the entire surrounding environment for more than a few tiny microseconds, and then flawlessly reversing it, is a technical nightmare light years beyond what we can do. Still, for an astronomer, this line of thinking matters. Even if total quantum revival stays out of reach, hunting for strange interference or anomalies in decoherence keeps the cosmic mystery alive. Finding a single deviation from our standard models could either crush the many worlds idea or offer indirect proof, depending on what the anomaly looks like. Another path is to judge these theories by their internal, logical consistency. Many worlds doesn't struggle with the measurement problem. It doesn't care what counts as an observer looking through a lens or when collapse occurs. It respects unitarity, the golden rule that quantum evolution is always deterministic and reversible. These aren't just minor perks, they are deep markers of harmony, which, in a field as exact as quantum mechanics, carry the weight of gravity. Yet this many worlds view demands a massive philosophical shift. It asks us stargazers to accept a cosmos infinitely larger and more complex than the space we see. It shatters the comforting idea of one single, objective reality shared by everyone. It suggests our sky is just one thread among billions, and everything that can possibly happen does happen, just out of sight in another branch. This scale is unsettling for many. It seems wasteful and it feels completely untestable. But maybe the true hurdle isn't physical, but inside our minds. Our resistance to this multiverse might just come from the overwhelming strangeness of what it means. We are wired to see one timeline, fixed events, in just one version of ourselves. A cosmos that fractures endlessly, playing out every single possibility, completely defies human intuition. And yet, gazing at the stars reminds me that nature never cares about our intuition. From bending starlight in relativity to quantum entanglement, reality is always stranger than fiction. Maybe the many worlds theory is simply our next leap forward, a way to take the strange laws of quantum mechanics absolutely literally. Can you and I actually test this multiverse? Strictly speaking, perhaps not, but in reality, we already are. Every time an experiment confirms these quantum rules, every time a massive superposition fades exactly as predicted, every time a quantum machine solves what a normal computer simply cannot touch, we prove the consistency of a cosmos that behaves exactly as many worlds describes. The final proof probably won't be one sudden, dramatic telescope observation. It might emerge slowly as older theories burn out, as physical collapse models fail, and as the pure elegance of a branching universe becomes impossible to ignore. Ultimately, we might embrace it not by seeing another world, but because we find zero reason to doubt they're out there. We may never see the other branches. As astronomers, we may never touch these distant sectors or cross their borders, yet the silent, precise cosmos keeps evolving as if they truly exist. And if the astrophysics equations confirm them, needing no extra assumptions or sudden magical collapse, no hidden variables, perhaps that's enough. We observe just one branch, we remember one past, but the physical laws shaping our night sky shape all the others. The multiverse doesn't need our permission, it only requires our curiosity as observers. In the quiet rigor of quantum theory, multiple worlds endure, not as science fiction, but as a completely natural extension of our mathematical models. We might never build branching machines or catch glimpses of our alternate selves, but it offers something much subtler. A cosmic framework where the strangeness of quantum mechanics becomes absolutely inevitable instead of deeply mysterious. It invites astronomers to view probability as identity, our telescope observations as entanglement, and choice as structure. In that starry light, every lab experiment is already a test, not of other distant worlds, but of the very one we currently inhabit. Chapter 10, When Modern Physics Suggests Multiple Realities. In classical science, our view of reality was beautifully simple and entirely singular. We tracked one single universe, governed by absolute laws, unfolding in a fixed, highly predictable celestial dance. Our lenses revealed an objective, shared, singular space. but the stunning arrival of quantum mechanics completely shattered that old picture. It swapped certainty for probability, rigid determinism for amplitude, and clear starlight for shifting superposition. As we explored this strange new frontier, it became clear that reality, at least as mapped out by quantum theory equations, might not be singular, but actually vast and many. Interpretations vary, but the math itself whispers a profound secret to us. More than one version of this reality can exist. Not just theoretically, but unfolding simultaneously. The deep math of quantum mechanics doesn't actually demand collapse. The wave function evolves smoothly and deterministically, rippling outward across all possible cosmic outcomes. When we aim our telescopes at a system, the equations don't isolate one result. They hold every possibility. It's our own human interpretation, not the theory, insisting on a singular view. This is where the many worlds interpretation draws its immense power. It never attempts to rewrite quantum mechanics. It just accepts the wave function at pure face value. It dictates that if the math includes all outcomes, so does the universe. We don't need a rule to pick one result. Instead, our reality splits, not visibly. Not violently, but mathematically, branching into new versions, each consistent, isolated, and incredibly real. You and I are looking at one of the most radical ideas in the entire history of science, a universe refusing to reduce itself to a single outcome. Yet it also remains one of the most beautifully parsimonious. It totally removes the need for weird collapse mechanisms, human observer rules, or hidden variables. It preserves the absolute purity of the equations, letting them describe the whole cosmos in full. The many worlds theory is the most direct expression of this concept, but it's hardly the only place our physics hints at multiple overlapping realities. In my field of cosmology, inflationary models point to bubble universes, isolated cosmic regions boasting entirely different physical rules. Over in string theory, the underlying math holds an unfathomably vast number of possible vacuum states, each one potentially birthing an entirely different universe. Even black hole physics, with its information loss paradoxes and fiery horizons, occasionally implies observer-dependent realities that diverge in far more than just mere perspective. In every instance, the math heavily favors multiplicity, not because we physicists desire it, but because it remains the simplest, cleanest way to fix deep contradictions. Having more than one reality isn't just some poetic flourish. It's a genuine solution, one that fits our observational data, preserves natural laws, and maintains flawless internal consistency. Come with me, let's look closely at a striking example where quantum physics hints at a multiplicity of realities, the famous double-slit experiment. When we fire a single electron at a screen with two tiny slits, it leaves an interference pattern, as if passing through both gaps at once. But the moment we set up a detector to observe which path it takes, that beautiful pattern entirely vanishes. This phenomenon isn't limited to electrons. Photons of starlight, atoms, and even molecules exhibit the exact same behavior. Standard interpretations argue the act of measurement collapses the wave function down into a single, definite outcome. But the many worlds theory dodges that collapse entirely. Through this lens, the electron travels through both slits, just in entirely separate branching realities. One version of the observer watches it pass the left slit, another sees the right. That interference pattern emerges from the combined mathematical structure of the complete wave function. It's a deep cosmic structure reflecting multiple realities at once. Another striking mystery stems directly from quantum entanglement. When we entangle two particles, measuring one instantly defines the state of its partner, no matter how many light years apart they might be. Looking at the stars, Einstein's spooky action at a distance shatters our everyday intuition. But through the many worlds lens, no distant action is required. Every outcome simply happens. Each branch holds one path for each of us watching. Perfect alignment without needing invisible forces across the void. Even the idea of wave functions collapsing fades away. We astronomers never actually see a collapse. We just assume it happens to explain the single reality we observe. Yet if every result thrives in its own separate branch, nothing has to collapse at all. Instead, reality flows smoothly into coexisting versions. let's look at how cosmology takes this even further. In those early moments of cosmic inflation, the universe ballooned outward exponentially. Tiny quantum ripples were stretched across the cosmos, seeding the very galaxies I study tonight, but these seeds were purely quantum from the start. Under the many worlds theory, every single way those ripples could form birthed its own massive universe. The observable sky we map is just one reality out of countless others. And if eternal inflation is real, the expanding never truly stops. It only slows down in local pockets, forming quiet bubbles where space cools into matter and shining stars. Each of these cosmic bubbles might hold entirely different laws of physics, born from early cosmic fractures. These are not science fiction fantasies. They are fully expected by our best models of cosmic inflation. String theory deepens the mystery, suggesting extra dimensions folded up in ways we can barely imagine. It offers no single answer for the shape of spacetime or the rules of nature. Rather, it paints a vast, sprawling landscape of possible solutions. There could be 10 to the 500th power of them, based on how those extra dimensions fold. If our universe is just one star in this mathematical landscape, countless others might be just as real, shifted only by their starting conditions. And then we face black hole complementarity. To solve the information paradox, some colleagues believe information bounces off the event horizon and falls inside, all depending on who is watching. This points to an observer-dependent reality. Once again, multiple versions of events have to exist together. Not just in equations on a chalkboard, but in the actual fabric of quantum gravity. From my telescope to these theories, everything points to multiple, coexisting realities being absolutely necessary. Not because they feel philosophically beautiful, but because they solve cosmic mysteries we otherwise couldn't crack. Critics often say this is too wild. They argue that adding extra universes violates Occam's razor. But Occam's razor doesn't actually demand fewer objects in space. It simply favors fewer assumptions. If one universe demands hidden mechanisms and strange rules of collapse, while a multiverse just asks us to follow the pure math. Then the multiverse is the cleaner theory. Honestly, the real extravagance might be ignoring what the equations are screaming at us. If a wave function evolves naturally, carrying many different outcomes, and we've never actually seen a collapse happen, then perhaps denying the multiverse isn't being scientifically careful. It means we are just avoiding the truth. So what does this mean for you and I? If the cosmos holds countless realities, how do we live in ours? It means your life right now, so vivid and unique, is just one beautiful branch of a massive cosmic tree. The world we see through our lenses isn't fake. It doesn't lose value just because others exist. It's simply your path through this vast quantum forest. And even if you never cross the void to meet another version of yourself, the very shape of the universe is still guided by their gravity. The odds you calculate for events, the patterns shining through cosmic static, the pure sense of cause and effect we feel, all flow from the interference, coherence, and split of other possibilities. Your memories under these stars are real, your choices hold weight. But it isn't the only one. The physics of the night sky suggests reality is a living lattice, constantly branching, unfolding, and growing. Maybe this doesn't shrink our reality, maybe it finally makes it whole. A single universe is beautiful, a multiverse is inevitable. Ultimately, physics doesn't demand our belief, it only asks us to listen, and when the equations sing of infinite multiplicity, we are not staring at fantasy, but a much grander form of realism. One that embraces your life and all the others, not as a sci-fi story, but as the true consequence of taking quantum theory seriously. You and I may never step across the void between worlds, but we can accept being part of a cosmos rich enough to hold them all. If you are still awake, thank you for stargazing through this quantum landscape with me. Your trajectory through the cosmos tonight is just one of many, but it matters. If sleep is still hiding behind the clouds, another whole galaxy of wonders is waiting for us. Let the next video guide you even further into deep space. Rest well out there in the quiet nebula. Fellow stargazer.